Hello and welcome back to another video. In this problem, we're told a spherical balloon is being inflated and the radius of the balloon is increasing at a rate of 2 centimeters per second. So in part A, we're asked to express the radius of the balloon as a function of the time t. So this radius r is a function of t, and we're told that it's increasing at a rate of 2 centimeters per second. So it has a constant rate of change, which is 2 centimeters per second. So what we have here is a linear function. Right? Constant rate of change means linear, so we can write this in slope-intercept form. So we have the slope times our variable t. The slope we know is the rate of change, which we know is 2, plus the y-intercept. Right? The y-intercept, or the r-intercept, is the value of r when the other variable t is equal to 0. So this is radius when time is equal to 0, which is 0 itself because the balloon hasn't been inflated yet. So this is r of t is equal to 2t plus 0, or just 2t. Now we're asked, if v is the volume of the balloon as a function of the radius, find v of r and interpret it. So the volume, v, of r of a sphere in general is 4/3 pi r cubed. This is just the standard formula. What we can do is, since we have a function that represents the radius, we can do the composition v of r, which is the same as v of r of t, plug in our value for r of t, so this is v of 2t, and now we have a value which we can plug in for r in our v function. So this is 4/3 pi times t 2t cubed. Now we have a formula for the volume of the balloon as a function of time, which when we're asked to interpret this composition, that's what it means. Volume as a function of time. 2 cubed is 8. 8 times 4 is 32, so this is 32 over 3 pi. We've already cubed the 2, now we just have t cubed left, and this is your final composition. Again, it is the volume of this balloon as a function of time.